Thanks for hosting me. It's a great opportunity, and it's definitely, I'm hoping that I will be able to at least transfer some knowledge that we have gathered over the last few decades in different greenstone belts across times. Of course, you probably are quite familiar with greenstones of Neo-Archean age, but I'm going to try to spend half of my talk on those that you may know less about that are referred to as being of lower middle Proterozoic age and also called Rhaetian greenstones that we find mainly in West Africa and in the Guiana Shield. And we have the pleasure to have South American geologists visiting us this week. So we're going to try to honor some of the knowledge that they have shared with us over the decades. So we'll get started on that. So I'm going to cover a fairly broad range of topics. So hopefully I'm staying, say, in a dimension that you feel comfortable with. And if you don't, I'll be more than happy to take questions maybe towards the end, I would think, and certainly elaborate on a number of concepts that I'm going to cover. And I am definitely covering a broad range of topics. Sorry. Yeah. So I'm going to start with this. First of all, um, Earth dynamics is behind basically metal systems, as you know. And we are going to talk, if we're interested in metal systems, we need to appreciate the fact that they relate to tectonics in general terms. And these tectonic regimes over time have evolved. And that's mainly related to the fact that basically the Earth has cooled down and has basically expelled a lot of heat through time. And it's this heat, basically exhaustion, that has dictated the motions at the surface of the planet to create, in part, greenstone terrains. And we're going to try to see some evidence of that. So most of this activity, which relates primarily from the early stages of Earth's formation to plume activity, and so these are basically very hot magma that comes from way down there from the core mantle boundary, has actually been rising through the mantle and producing a lot of turmoil and a lot of crust at the surface and producing a lot of rocks that we're going to see today. And those are related to these systems. So plume activity in particular, which is a really important topic for the formation of greenstone terrains, basically decreased very significantly about 2.7 billion years ago. So there's about a 2 billion period where there's a lot of plume dynamics, and around 2.7 it starts changing, and we'll appreciate that it's going to slow down as time progresses as well. And we'll see that that's reflected in part in the stratigraphic records of greenstone terrains between Neo-Archean and Middle Proterozoic ages. Another really important concept to keep in mind when we're thinking about these mineral systems and the formation of greenstone terrain certainly is the fact that land masses at the surface of the planet have come back and forth, right? So they have migrated as they do today. And every so often they meet up and they basically merge and they amalgamate to produce what we call supercontinents. And these supercontinents are very important to retain heat underneath them, but also it's when they break up that we're really interested because the breakups and the assemblages of these superterrains produces manifestations that lead to mobilizing metal, but also mobilizing magma and creating deformation. So those concepts are all very important to us to track mineral systems, and we'll reflect on that as well today. Another very important concept altogether is the concept of lithosphere. So there's a continental lithosphere. All continents have some lithosphere underneath them, and this lithosphere is very variable from places to places. And I'll show you a map in a minute. And this lithospheric configuration or the nature of the lithosphere has strong influences on the overall metal systems as they progress through time as well. One thing that is really important to know is that the majority of the continental surfaces today or continental masses are underlain by Archean lithosphere. So all the continents have very old rocks in their basement, and that's a very important concept because the Archean provides most of the gold to the planet early on. So therefore, we have a lot of old gold in the lower crust and the lithosphere itself. So today we're going to focus on two time sequences that are absolutely critical in producing greenstones, and we'll try to appreciate whether they're analogous or not, and if they're different, in what fashion. I'll touch just on a few differences that are quite significant in my opinion, and we'll keep it at a high level for the moment. First thing we need to dive into, or at least appreciate, is that basically there's been a lot of gold produced on the planet, but it starts definitely in the Archean. So in this diagram on the upper left, you clearly see basically the abundance of gold through time, and you can appreciate that there's two prime cycles that are labeled Near-Archean and Rhaetian, which are the subjects of today's presentation, that are producing a lot of gold altogether. And then there's going to be more gold produced during further cycles, during basically various tectonic processes that are caused by the collision of tectonic plates that produces a lot of these mineral systems. So there's three principal periods where there's a lot of gold produced on the planet, and I'm going to talk about two of them in a very simplified fashion, the Neoarchean and the Rhaetian. And later on, during modern plate tectonics, of course, and currently, we're producing a lot of gold. You may know that there's a lot of gold produced in Asia right now from a lot of modern plate tectonics, but I don't have time to talk about those particularly today. So let's focus on the Neo-Archean and Rhaetian gold, and we'll try to compare some elements between them and understand how the gold is distributed in them, and we'll try to illustrate a couple of deposits, districts, and also deposit types and specific deposits that illustrate some of the concepts that I would like to share with you today. We will ask ourselves whether the gold through the formation of these Neo-Archean and Rhaetian greenstones are related to similar geological conditions. Do we have exactly the same conditions between the Neo-Archean and the Rhaetian or not? What are those differences? And we'll list up a number of criteria that we would like to compare. And then we'll ask ourselves, of course, is there's as much gold between the Neo-Archean and the Rhaetian? The answer is already addressed on that compilation, which is already dated. I mean, that's about 20 years old now. The Rhaetian contains less gold so far than the Neo-Archean. So if you're looking for gold absolutely in greenstones, you're better off looking for gold in Neo-Archean greenstones. However, there's more and more endowment being found in Rhaetian greenstones, and I'm hoping that I will be able to convince you that it's worth pursuing exploration efforts onto it. Oops. Sorry about that. So how do they compare in a very general sense? So I'm taking here two snapshots, two figures from on the left side from the Superior province. So that's basically where the largest exposure of Neo-Archean greenstone belts on the planet, literally. So you see basically their distribution, their spatial distribution, how they're organized and all that. And those are the main constituents of these greenstones. So they're made of volcanics primarily, and they're made of continental sediments and oceanic sediments as well. So those are the three main constituents of greenstone belts in general. And you see that in some cases, some of these supercrustal rocks or this assemblage of rocks are concentrated more in certain areas than others, like the Abitibi, for example. That's definitely the largest concentration of greenstone rocks. And so that's basically a pattern that we're quite familiar with in Canada, and Sudbury is right there at the south end. One thing we should keep track of, or certainly be aware of, that is there's a timing evolution of the making of those greenstones in time. In a very crude sense, we can say that across the Superior province, the older greenstones started forming way back when. The first ones date back to 4.2 billion years ago. So we were already forming these kinds of assemblages of rocks at 4.2, but the majority of them are going to peak around 2.7 billion years, roughly. And those are mainly in the southern part of the Superior province. So those are the ones that actually contain the most metal for the moment, certainly for gold. And I'm drawing your attention to now a Rhaetian greenstone terrain, which is West Africa. It's the one that we know most of right now. There's more of them that I'll talk about in a moment. But this is by far the largest surface area that contains or has Rhaetian greenstones in it. It covers pretty much all of the West African countries, from basically Senegal all the way across to we're looking at Ghana. So we're looking at a very large landmass. Those two pictures are at the same scale at the moment. So I'm trying to compare them exactly at the same scale to show you roughly how basically these greenstone rocks are distributed spatially. So you can see that there's roughly the same patterns between the two terrains, but I'd say you'll probably notice right away that there's more gray on the map on the right, which is basically telling us that there's a slightly different stratigraphic signature to the Rhaetian greenstones than there is in the Nearchean ones, and I'll touch on that in a moment. Another feature I want to draw your attention to is the sort of architecture. It does resemble at the same time, because they are the same scale. I'm sure you probably appreciate that the size of the, say, the linearity of these belts, the extent of the belts themselves, and the fact that they're quite elongated along strike, we call that the structural grain of the greenstones, is a bit more extensive on the Rhaetian side than it is on the Nearchean side. And there's a reason for that. So I'm going to try to elaborate on why that is. Another really important feature that I want to draw your attention to, and that's what I've labeled on that map on the right, which is called archons, right? So why do I call them archons? Because they're basically Archean landmasses. So they're vestiges of Archean rocks, like those on the left side, but those rocks drifted away at some stage from a supercontinental breakup, and they basically split. They split up, they just rifted, and then one day they converged back again. So the material that was formed between those Archean land masses produced basically the architecture of the Rhaetian greenstones, and we'll try to familiarize ourselves with the components in a moment. So where did these, so this is a reconstruction you may have seen in some publication. This is the latest compilation produced by Wouter Bleeker from the GSC. And so Wouter has now basically, after years and years of great efforts, trying to basically demonstrate to us basically what how the Archean land masses were at some point potentially assembled. So the outline is this large piece of land right there called basically the Supercraton Superia. And this is basically how all these Archean terrains were potentially assembled towards the end of the Archean and in transition to the Rhaetian times, right? So that should have been the snapshot or the picture. If you would have been there, you would have been, say, in a shuttle, you would have taken a picture of the planet. That would have been a supercontinent of the time. And what I want to draw your attention to are two things. Principally, is that Wouter is now of the opinion that you've heard probably that the Yilgarn in Australia is in a time fashion at least comparable to the say Superior Province, or in age and in compositions potentially. And people have been debated where it would fit back with the Superior Province. Well, there's Wouter's latest suggestions or proposal. Sudbury is down here, right? So we're down here, that's where the Abitibi is. And so what he's suggesting is that the Yilgarn would have been that one landmass, basically fitting back to the very south northwestern corner of the Superior Province. So therefore not really lined up with the southern province, more like the northwest. So that's a great proposal. I'm not going to dwell with that, but that's an interesting suggestion, at least for those who want to correlate the prospectivity of those terrains between the Yilgarn and the Superior Province and the Abitibi in particular. So that's one aspect. The other point that I want to draw your attention to is the distribution, or the gaps that are formed around, basically that are left around this reconstruction, which could have been places where these Rhaetian greenstones could have been born. So they're born from the breakup of Archean terrain. So where could we eventually fit them back in? And where would some of these Archean land masses that are currently present in these Rhaetian terrains, where could it fit back in? So there's multiple options. I've decided to show you three or four of them, but it could have been anywhere around. I like this one in particular because it sits not too far away from the Superior Province and basically the Abitibi, which is right here. So this is maybe where some of these greenstones of Rhaetian age were formed. So not far off from very well mineralized greenstone terrains of the Archean times. They could have been forming anywhere else, right? So we don't know exactly, but we're eventually going to be able to reconstruct them. But what the key message out of this picture would be that basically these Rhaetian greenstones were formed off these Archean landmasses that basically rifted away, and some of these Archean landmasses are themselves potentially mineralized. And as I was telling you, a lot of Archean rocks, Neo-Archean rocks, are forming the roots of some of these terrains, and therefore they could be some Archean metal at the basis of some of these Rhaetian greenstones themselves. So is there potentially an association or a link between the metal endowment of Archean landmasses and Rhaetian ones? So if we compare in a fairly crude sense, say a general stratigraphic column, so we're trying to here more or less observe very rapidly the barcoding, as we call it, of, say, a typical greenstone sequence of Neo-Archean age versus a Rhaetian one in general terms. So I've picked up, say, a summary. This is not a stratigraphic column in particular, it's just to draw a picture really for you in general terms. The, the column on the left would represent, say, the majority of the constituents of an Archean or Neo-Archean stratigraphic sequence. I want to draw your attention to the fact that it's dominantly green, right, and purple. So it's basically it's a combination of very mafic, ultra mafic volcanic rocks and a lot of mafic rocks that are somewhere bimodal and evolving into more felsic end members in the yellows. But it's alternating, and we know that there's multiple cycles. There's really good research conducted on most of these greenstone terrains that suggests and really clearly support the idea that most of those greenstone sequences alternate in what we call juvenile tholeiitic source, mental source magmas, and they evolve with time by contamination somehow in multiple cycles. So 7 to 8 cycles have been documented, for example, in the Abitibi. But it's dominantly greenstone rocks, it's dominantly green rocks, and it's dominantly volcanic, mafic volcanic rocks. Capped by sediments potentially, and those sediments were formed under oceanic environments. So therefore, that's the next stratigraphic sequence of significance. And once that is formed in a fairly extensional environment, so rifting away, literally basically filling basins, then eventually one day that terminates, and you're no longer spreading volcanic rocks, you're no longer creating deep water sediments. Then there's an inversion, or the basin cease to operate, and they're inverting. Therefore, eventually they start colliding and closing, and that leads to slight reliefs, or basically you're creating some erosion of those rocks, and eventually produces what we call terrestrial sediments at the very top. And you're most familiar, I'm sure, with the term conglomerates, polymic conglomerates, which are formed under those circumstances from the erosion of everything else that precedes them. So that would be a typical stratigraphic column for the Neo-Archean, right? So that's what we're going to map out there pretty much everywhere Archean greenstones are preserved. If we now step into a Rhaetian domain, I think we'll notice relatively rapidly that indeed we have the same color schemes, but there's definitely more gray than there is green. And there's one color missing altogether, and it is fairly factual. We know that for quite some time now, and we've been looking for these rocks. We just can't find them. They're missing the purple color. right? So we're losing the Komatiites. The Komatiites are not present in the Rhaetian greenstones. And that's a key, that's a very important message. That means that we're missing basically very hot magmas. So the planet is cooling down seriously. By the time in Rhaetian times, basically it's basically half the heat that it was actually expelling back in the Archean. So therefore, greenstone terrains are reflecting that. We're no longer able to produce basically the magmas that were produced under very hot conditions. So our komatiites are gone. So we're not dealing with them. But however, we still basically find all our mafic volcanics in cycles as well. However, we don't have this sort of alternating cyclicity that is more typical of the Archean greenstones. We're dealing principally with a tholeiitic base, literally. So it starts off, the mafic volcanic start with a tholeiitic sequence, and it evolves into calcatoline sequences that are quite thick, very substantial and quite thick and not very much differentiated, with some bimodalism to a certain degree. So that's why you do get a little bit of yellow in there. But what's really dominating all of a sudden is once the volcanism is done, we will now deal with a lot of sedimentation. And the sedimentation will be more voluminous and more extensive and more diversified as well. We'll be basically dealing with 4 or 5 different environments of sedimentation altogether. Most of them are analogous to the Archean ones, but some of them are more specific, they're more enclosed. Another rock type that you notice on this column that is not reported in Archean greenstones is limestones. So very locally, all of a sudden, we're finding in some places in West Africa the presence of limestone rocks. So that's telling us basically that we're dealing with hotter waters, hotter conditions, and there's oxygenation that is starting to allow basically living creatures to develop themselves on these platforms on the margins of these old continents. So limestones are going to be participating to stratigraphic records, and we'll have also manganiferous shales and a lot of carbonate shales locally developing as well. So our stratigraphic column all of a sudden becomes very sedimentary and quite volcanic, and we'll see basically what that looks like in on a map. What is the Rhaetian like? So it's 600 million years younger than the Neo-Archean. So the Neo-Archean was a pretty toxic time. Basically, the hydrosphere and the atmosphere was extremely toxic, loaded with carbon dioxide. All of a sudden, we're starting to see a little more oxygen that is starting to form. And we're just past a very critical stage in the evolution of the planet. We've just gone through a cycle of basically snowballing effect, as we call it. So the planet was covered with its first ice shield at about 2.3 billion years. So from the Archean now, we've gone through the snowball event that will eventually help changing probably some of the chemical conditions in the hydrosphere and the atmosphere in general terms, and it will polish the surface. It will take care of polishing all the older rocks, right? So it's now going to produce a lot of erosional products that will contribute to produce some of our sediments. Another really important, so therefore one of the manifestations of that particular period are the beautiful diamictites of cobalt. So I'm sure you're familiar with them, not too far from here. And what's interesting is that those are the first sediments basically forming at the start of the Rhaetian. So the Rhaetian starts with the glacial period, right? So, and those glaciers are basically drifting off the erosion of Archean land masses. And as you know, the cobalt diamictite is actually sitting right next to beautiful gold deposits, not far from here, about 4 hours north of us. There's actually a beautiful sequence sitting right next to Makassar, or not too far away from it, that has probably collected some gold in its making, and some of this gold is eventually transported into these sediments and eventually transferred into our Rhaetian environments. So what I'm trying to tell you is that some of the sediments that are produced during the Rhaetian period are probably inherited from the erosion of older sources of metals. So they're starting to collect on their own and they become potentially a metal source. I'm not saying it's the metal source, but it's certainly a new element that will add to the story. And finally, the Rhaetian ends at about 2 billion years ago, with the beautiful Bushveld layer complex, which is the largest layered complex on the planet. So it ends with a very pronounced plume event that actually affects and produces its own geological character. So that's a great metal system that develops at the end of the Rhaetian. So Rhaetian dynamics, if we can summarize them, basically all of a sudden our atmosphere is changing and we're dealing with reducing atmospheric methane in the environment. And all of a sudden we also have aerobic microorganisms that are starting to colonize the environment, producing limestones, blah, 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 and transforming and fixing some of the metal for us, and eventually even creating a lot of oxide minerals. This period of time, we're producing 2,400 new oxides on the planet. So it's the first time that the planet is actually creating a lot of oxides. So that's a very important character. What does the planet look like back then? This is my funny picture of it. Basically, this is the way I sort of envisage it. It's floating archons that are basically separated by rift zones or extension zones. Uh, the tectonics of the time are probably dominated still by what we call the lid effect. Those land masses are navigating and expanding on the planet. However, they're large now. These cratons are of a significant size, and they will interfere with the tectonic regime. So now we're spreading the crust. Yes, we're creating these big rifts, we're creating these big basins, but these land masses are big enough now to induce their own tectonic regimes around them, which is something we didn't have as much of back in the Neo-Archean. So there's a new player in town that is now going to change the character of tectonism around itself, and we'll see some manifestation of that in a moment. One really important consequence of the presence of these land masses is almost like you see in modern plate tectonics, is that these archons, and this is a cross section of it right there, they are now going to help forcing basically some of these basinal or extensional basinal stratigraphic packages, the volcanics and the sediments, to ram over them. So right forcing subduction, which will occur, there will also be some thrust tectonics all of a sudden. So our style of deformation is also going to change on us. We're going to see the first full thrust belts forming at this time. So let's go back to a map of a typical map of the Neo-Archean greenstones. Again, this is the best documented one, so we're all familiar with it. What it means is quite simple. It started with a lot of volcanism. 6 cycles are documented. What's really important is that this volcanism lasted about 40 million years. So there's a lot of extension, there's a lot of expelling of magmatism, and it lasts about 40 million years. So it's quite fast. It's very fast expression, it's very fast extension. And then eventually one day this gets inverted. It's of course volcanics and sediments all together. And then it closes back on itself. And as it closes back on itself and starts to converge, we're producing these structures. So all these red lines and all that, those big faults, are producing by the inversion of all these volcanic rocks and sedimentary rocks together, and you're starting to form that beautiful framework bounded by a lot of faulting. So that's happening relatively quickly. The cyclicity of the convergence, so we have about 40 million years of production of volcanic rocks. The inversion and the contraction itself that produces the faults is extremely rapid. It takes about 10 to 20 million years. It's extremely rapid compared to modern plate tectonic regimes, which last 200 million years. So this is extremely rapid dynamics. Let's go to the Rhaetian now. Same landmass I was showing you, same distribution now. So you're seeing basically the constituents. Again, the same thing. We're dealing with starting with totally basalts and evolving into calcareous volcanics. And we're seeing that they last now a little longer. We're talking about 80 million years of magma production. So all of a sudden, our cycles are a bit longer in terms of magma production for the mafic ones. Then it's followed by basically a cycle of sedimentation once the magmatism is done. And we see there is a migration of, say, a time migration of the production of the mafic volcanics from the northeast corner of Ghana towards Mali. The sediments are doing the same. They're following the same cycle in the same direction, and they're laying over top of these volcanic rocks. And then finally, on top of it, in the yellow in this chart on the right side here, you're now seeing basically the evidence of emergence of both the volcanic rocks and the sediments on top of it. And we're producing mountain belts or mountain chains, and they're starting to erode and they're forming this beautiful veneer of plastic sediments of alluvial origin. So now we're assisting at this erosion of these greenstone terrains. But keep in mind again, remember, we have these large Archean landmasses, particularly the one on the left here in Guinea, which is really large. And we look at the scale here, that's about 200 kilometers. So that landmass on the left side here is Neo-Archean in age, and we'll see its implication in a moment. So that's for the stratigraphic records. So we're now appreciating that there's slightly different, there are some slight differences, right, between the Neo-Archean greenstones and the Rhaetian ones. From a magmatic perspective, from a plutonic perspective, I'd say, generally speaking, we're looking at roughly the same type of evolution from a plutonic production itself. So we'll have some plutonism that will be produced by partial melting. We'll have TTGs, we'll have granites that are getting more and more hydrated with time. One thing that is very clear is that through younger cycles, they're getting the plutons themselves are getting more and more contaminated. They're getting more and more potassic. And as they do that, they're transiting from what we call a crustal growth stage to an accretionary stage to a reworking stage. And these plutons are going to be eventually fertilized and fertilizing the host rocks that are accompanying as they actually come to surface. And once you tectonize them or you strain them or you deform them, these metals are going to come out of some of these intrusive through time as well. In terms of the mafic magmatism, it follows exactly the same sort of patterns that the Archean mafic rocks were doing. They're transiting from a morb-like or an oceanic crust-like condition to a transitional. There are no true arcs formed. It's like transitional between arcs and morb-like situations that are producing large plateau sequences. That's for the volcanics and the intrusions, Rhaetian ones. So in a general sense, oops, sorry, I need to go back. Oh, I had an animation that doesn't come up on this one. Okay, I'll put it. So if we now compare again those architectures between the Superior Province and the Rhaetian West African condition, this is roughly speaking basically how things are comparing in terms of architecture, in terms of stratigraphic distribution. So you can clearly see that there's a framework, a structural framework developing quite nicely inside the Rhaetian terrains. But I would like to draw your attention to scales here. So if we think, for example, let's just look at, say, the large structures of the southern Abitibi, like the Cadillac or the Lake, which is 250, 300 kilometers long, substantial architecture, substantial structures. Well, you now, unfortunately, the legend is very difficult to read here, but some of the faults now that are forming in this terrain are 1,000, 2,000 kilometers long. So we're finding really all of a sudden we're creating much larger structures at once of the same general type, but not necessarily of the same magnitude. And that's another really important point I want to make through the presentation in a moment. Another point I would really want to draw your attention to is the relationship between the large Archean landmasses and these Rhaetian greenstones. You can clearly appreciate that there's a texture developing around the Archean landmasses. There's a clear interference, there's a clear influence of interaction between the Archean landmasses and the surrounding greenstones that were formed before them. So now we're clearly going to call upon the interaction between these rigid rocks and the creation of structures all around that. We don't have that much in the Neo-Archean, right? So in the Neo-Archean, we have a few older terrains that are interacting, but altogether, it's almost like an isotropic package of rocks. So basically, it's all more or less the same rocks that are converging back and forth together. So there is contrast, yes, but the main contrast in the Neo-Archean is between the granites and the surrounding rocks. That's really where the majority of the contrast and competency are. So the rigid rock, the granite, and a lot of volcanics around that. All of a sudden, we're introducing much larger land masses. A picture to maybe refer to or an analogy is this is almost like India running gradually, or like a large, say, condyle mass that you can think of that eventually rams into volcanic rocks or in a volcanic terrain. So consequently, there's going to be more architecture, more faulting, and it'll be a bit more dynamic because this Archean landmass comes from a long ways away. The terrain we're looking at here is about 2,000 kilometers across, so it's very large. So we had a large oceanic basin, if you like, the size of the Atlantic maybe, that shortened, and then basically Archean land masses converged back, and they're now going to produce their own architecture around them. So different styles and definitely larger structures altogether. So the nature of the tectonism, the nature of the structures is also going to evolve on us. We're starting, say, the first greenstones that were formed, apparently were formed, I mean, certainly as reflected in the Pilbara, they were formed by what we call vertical diapirism or gravity changes, gravity transfers between heavy rocks and light rocks, between melt rocks as well. That produced basically what we call the vertical distribution of, say, CTGs and the surrounding greenstone. So the very blebby aspect of the Pilbara, for example, gradually with time, this evolves into a more linear organization of the supercrustal belts, like the Hobe belt as an example. Lots of other greenstones are having exactly the same shape. And that's an evolution in the tectonic pattern, right? So you see that the structures are evolving with time, they're more linear. However, I insist in saying that they're quite restricted in length. And they're restricted in time as well because they don't last very long. It takes about 20 million years to form that pattern in the Neo-Archean. In the Rhaetian, we're doing the same thing. However, now we're going to have to play with the archons in our way. So therefore, there's going to be different patterns and there's going to be more activity, and the length of deformation or the time of deformation will also increase. So now we'll have 40 million years, we'll have 50 million years to start shoveling the rocks around. So it adds a time factor that I think is important to create some of these metal systems. And this is just a cartoon to sort of illustrate, say, the various modes of operation of some of these structures. So on the left, we have basically a reproduction of the mode of formation of the Cadillac break, for example, on the Quebec side. So on the left side, you have sediments of the Pontiac group, and you have all the volcanics on the north side. And they were separated at some stage by, say, ultramafic rocks that relate to plume activity that was probably rifting this terrain. And then one day it gets inverted and produces a beautiful structure called the Cadillac Larder Lake, of course. And it focuses on this sort of an interface between the turbidites and the mafic rocks. So it produces a big structure, but that big structure is now focused on a very important rock, ultramafic rocks. These ultramafic rocks, these komatiites, play a fundamental role in the story because they are extremely amenable to deformation. They're very ductile, we call them, and they're transforming basically into a rock mass that is very, very brittle, that produces a lot of fluids, and that eventually captures a lot of fluids as well. So it becomes a really important receptacle for all the activity that actually forms around them, including the intrusive rocks that are shooting right along those structures. So all of a sudden you create a beautiful corridor that focuses all the fluids and the metals to them. In the Rhaetian, we don't have ultramafics, so we cannot produce a structure like the Cadillac break. The Cadillac break is unique to Archean times. very clearly because of the ultramafics in particular. So if we're looking at structures in Rhaetian times, we have to reflect on other modes of mechanisms, other modes of operation. We have them. They're there. They're very clearly there, but we cannot use basically all the prospectivity criteria, all the criteria we're using for the basically the prospectivity of the Cadillac break to say, oh, let's just import them straight over to the Rhaetian and let's play the same game. Let's use exactly the same principles. We cannot do that. We have to adapt basically our lines of thinking and our lines of prospectivity to the scenario under which these structures were formed. And here's one cartoon that I'm proposing for this area. I don't say that that's necessarily the final word on it, but my view of the Ashanti trend, which is as endowed as the Cadillac Larder Lake. So we have as much gold produced in Ghana than along basically the Abitibi trend. So same endowment, but very different configuration. That's the key message. The sort of cartoon or sort of idea behind it is that you see there's gray rocks and green rocks on one side and there's pink rocks on the other side. What I'm proposing is that basically you're dealing with a big rift or a big fault that formed on the edge of a continental mass. So basically you're on the edge of an Archean craton. It failed, it rifted, and then someday the rocks basically came back. So it's an inversion of the volcanics and sediments that formed offshore from the continental mass, and they came back and ran over and were reactivated multiple times and created a big corridor of deformation, but a very different regimes, different rocks than the Cadillac Break. So yes, we have two big structures, but their origins are very different. Their evolution is very different, and their chemical relationship with the mineral migration itself will be very different. So they'll have slightly different modes of operation, different chemistries, blah, blah, blah. So therefore, you have to adapt your formula, you have to adapt your search factors to those conditions to predict where the gold might actually live on those structures. So on the map, they look the same, but in reality, when you check the rocks on either side, you realize that they're very different stories, and yet they're as endowed from one another. So we're going to Kirkland Lake very quickly, just to appreciate one factor and one point that has been made multiple times by many, say, researchers and general mappers in that sector. One thing that you notice right away is that basically it's a pretty complex story. The first thing that is noticeable here is the fact that the stitch line, which is the Cadillac Larder Lake trace, cuts across stratigraphy. So that structure itself is not bounding stratigraphy like the previous story I was telling you. This one is actually cutting across, and it's cutting across for very good reasons. If you look at the architecture, if you honor a lot of the work that has been conducted all around this part of the world, from mag data, from mapping, et cetera, you realize that this area in general is full of structures of all kinds. It's not just the one structure, not just the Cadillac, the Larder Lake structure. It's basically surrounded by a very complex architecture. To keep it simple, the volcanic rocks that are actually running, generally speaking, along this green line, okay, on this area. So that's the trend of the bedding. This yellow line, this red line, this other red line, that's the trend of all these thin lines that I've drawn on this map. And all those thin lines are themselves cutting across the volcanic rocks. This is dominantly volcanic rocks. But you notice that that pattern of faults is actually running at a high angle to the bedding, which is the green line. So all of a sudden, I'm having a very high angle relationship between rock faults that are running at a high angle to the bedding. So the strata themselves are dissected by faults that were there at the time of volcanism, probably. So we're looking at probably a pattern of growth faults that were formed during the creation of all this volcanic activity that then eventually, once I constrain it more, once I basically invert this terrain, that those old faults, really old faults, get reactivated and eventually they interconnect to one another and become a through-going structure. So the big structure is born from miniature or smaller scale structures that were all at some point assembled and connected to produce a large scale fault. That's commonly how faults are born. That's commonly how they will eventually recycle themselves. So it's a great lesson learned. Normal faults or faults that are formed during creation of volcanic sequences and sedimentary sequences are commonly recycled. And therefore, that's why they're reactivated through time, and that's why they become very prospective. Notice that, of course, the mineral systems, the CASA, are living on what people call a second order structure. I would call it a first order, like an old fault that got recycled through the process before probably even the large lake developed. So that's a very interesting part. The concept here is to live with the idea that there were a lot of faults already formed in the volcanics and the sediments that got reactivated in the Neo-Archean. Does that work in the oh, sorry, I forgot to put the conglomerates on top. Then, of course, these structures, which all culminate, they're all converging in this general sector. They sort of reactivate one another, and they create a depression potentially, and that depression gets basically filled with surrounding materials that produces these beautiful conglomerates. And there's a lot of reactivation on the faults all around this sector that eventually are allowing some plutonism to poke through it, and the alkalic plutons can eventually merge through these particular sequences because you have a big flexure in the structure, but that's a secondary product of the whole process. It's not a first order, it's actually secondary to the whole story. So, do we have something like that happening potentially in the Rhaetian? We do, but it's a slightly different story. Before we go there, though, I want to compare at least some of the physical evidences of strain and the nature of faults between a Neo-Archean fault and a Rhaetian fault. And here are the two best examples I can think of, which are both basically living in the middle of the maximum endowment of their respective times. On the left side, we're talking about basically the Cadillac break, so one snapshot right into it, where there's a lot of gold around it. And on the right side, there's the Ashanti shear zone, which has the same or equivalent endowment. I think you'll notice, I mean, unfortunately, the scale is not the same, but I think you'll notice there is a bit of a difference. This terrain or the strain here, the amount of deformation, the intensity of deformation, impacting, influencing conglomerates and ultramafic rocks, stomatites, is intense. It's really, really high strain. It's extremely one of the extremes, really, when you think of it. On the right side, this is about 50 meters wide. Okay, these are black shales, completely different rocks, right? So completely different. The faults are of different origin. They have different manifestations, and therefore they develop strain differently and they mobilize fluids differently as well. Because as soon as you strain a commodite, and as soon as you strain a conglomerate versus straining a black shale, you will not have the same product. You will not have the same manifestations in a thermal way, in a metamorphic way, whichever way you can think of. So necessarily those two structures are born differently, and they will have different reactions. They have different modes of operation. Another really important factor is that the black shales on the right here, they are saturated with arsenopyrite. They are saturated with arsenic and saturated with all kinds of other sulfurs and sulfides that are eventually going to contaminate the system and even source the system with their respective gold content, which gets mobilized. So in other words, very different recipes. Yes, we have its structures. The magnitude of this structure is about an order of magnitude smaller than this one, and yet you're still creating a big deposit with it. So there must be a multitude of mechanisms behind that that allows basically the mobilization of gold under different circumstances and different conditions. Here's some of these big structures. That's the Ashanti fault that I just showed you about. So the big photo was right in here. And that's basically the sort of the map pattern that it it actually delivers. It looks like a Cadillac brake if you just look at it on a map, but the nature of the structure is already revealed by the geology. If you look at it, it's basically blue against green rocks against pink rocks, carbonaceous sediments, and conglomerates on both sides. There are no ultramafics, so this structure is born differently, and yet it does have a lot of endowment to it. Basically revisit that. And there's exactly a similar scenario, in the Guyana Shield on the left side here, this image. You see it's roughly the same map patterns, the same colors, same sort of general geometry, and yet this structure, which has the same flank, this is exactly at the same scale, those two structures have completely different endowments. The one on the left doesn't carry much gold at all, and yet they have the same origin. They're formed the same. So why is it that we have more endowment in that particular structure on the right than on the left? And we're both in Rhyetian rocks. So, in other words, to summarize that, structures of Rhyetian time have certainly similarities to those of Neo-Archean age, but they're different in their origin and they're different in their evolution. Therefore, you have to adapt your tools and your prospectivity to those conditions, I think, accordingly. Let's now visit the gold camps very rapidly. So we know that in the Superior province, we have two prime gold camps, of course, the southern one in a Red Lake. They're about 500 kilometers apart. So that's where most of the gold lives. And it's around some of these structures that are themselves bounded by ultramafics most of the time. So that's definitely a very important parameter to reflect on. And most of this gold is related to magmatic and intrusion systems in general terms. So the majority of this gold is related and potentially sourced from these rock types in general terms, maybe a little bit of contribution from sediments as well, but it's mainly dominantly from these rock types that it is derived. That's the sort of a general distribution of say, mineral systems in the southern hemisphere. So we have the gold systems, we have the VMSs that are transiting across, that are living off different volcanic series, and we also have the nickel PGs that are tied up to some of these ultramafics on the very western end. We have a sort of general distribution of metal systems of the same nature in the West African Craton? Not really. There's still two very prominent gold sectors. The Ashanti Tract and the Kenyeva we'll visit in a moment. Well, there are no VMSs. There's absolutely no VMS occurrence at all in the Rhyetian. We didn't actually form them well enough, or just the favorable conditions are just not encountered. And the rest of the sort of mineral systems in West Africa is very widely distributed, and it is mainly around the Archean landmasses in general terms. So yes, we do have 2 or 3 hotspots in the Rhyetian. Just a reminder what some of the main characteristics of the mineral systems in the Archean are, or the Neo-Archean. We have here a segment of the Abitibi trend. We have 4 or 5 clans, all laterally from, say, ultramafic related, VMS related, low vein related, VMS or terminating, or let's say magmatic or intrusion related systems in general terms. So their mineralogy changes, and there's a clear progression from west to east in different sort of modes of operations and manifestations overall along the main structure, which is itself marked by the presence of ultramafic rocks. So that's a major profound boundary. So that's one mode of occurrence. Then we have the Timmins camp, which is focused mainly on the volcanic sequences, the interflow and the shearing between the various volcanic cycles that are producing a lot of carbonate, a lot of anchorite. You fold that package up, you create this huge megascopic folding, and eventually you start basically shuffling things around, and then you introduce also some plutinism and some felsic intrusions in it, and it injects itself and then helps mobilizing the gold into that large infrastructure in general terms, which is basically underlain by a broad fold package getting strained severely on the edge of a big structure. That's for Timmins. And we've touched on Large Lake, Kirkland Lake already. We've talked about basically this ramification of structures, the fact that the structure cuts across stratigraphy and eventually might actually inherit some of its hydrothermalism from that character. Do we have something of any of that nature in West Africa? Not really. We've already talked about Ashanti. It's mainly one fault bounding, basically the continental block reactivated on the margin of a sedimentary basin. So it's sediment dominant. So in general terms, most of the endowment here relates to sediments. So it's hosted in sediments. There's not really much gold in volcanic rocks as such. And there's not much gold. There's no intrusions. There's no felsic intrusions that are piercing through those faults that might even supply metal to these thicker settings. So where's the gold from? I don't have an answer for it, but it's probably from different sources or from different scenarios. We're going to visit a couple of the deposits in the Kenyeba window, where you see another trend, which is the next most down zone in westernmost Africa, and that's 2,000 kilometers away. So those are absolutely not connected. We're remote from this Archean terrain, but we're right on the edge of it, and it has an influence. It produces some architecture that will create some preparation for those deposits in West Africa. And here it is. That's the Kenyeba window. So we're now focused on the sort of district geology. It has volcanic rocks in contact with a lot of sediments. Again, this is entirely sedimental hosted. The peculiar aspect of this terrain or this stratigraphic package, sedimentary package, is that it's hosting these limestones that I was pointing out in the stratigraphic column. Those are going to play a fundamental role in the overall mode of deformation that affects them. So yes, they are strained. So many people, for long times, put a big structure right along this contact here, right along this stitch line. Well, that's the style of deformation. So this is not basically a big shear zone. You can see it's the same colors on both sides, right? If you just stare at the blue lines and blue shapes, you see that they're converging. They're not really offset very much. I mean, the strain is right there, right down the middle, but really this started life as a fold. So it's tight fold and it's normal because sediments are layered. So as soon as you start compressing the sediments, then indeed the sediments are going to start buckling, as we call it, and they'll get tighter and tighter strained. And as they progressively strain off, well, eventually they're going to develop some really what we call strain partitioning. So there'll be zones of preferred deformation, if you like, but that alone cannot create a deposit. Okay, you have to have an extra ingredient to the story, and it's pretty interesting in itself. There's a batholith right here, and that batholith basically altered the sediments before they got formed. So there's a sodic alteration that was basically derived from the emplacement of this batholith. So it injects itself into the sediments that are very permeable. They're taking all the magmatic fluids, the sodium that comes from the magmatic fluids, and guess where the sodium goes? It goes into the limestones, and it goes into some of the other sediments. It produces individual bodies of alteration, and sodic alteration is a hardening condition, as we call it. Now it's transforming the sediment into a very hard rock, right? So locally, the injection of fluids coming from the batholith are now transforming what we call the competency of the sediment. And guess what is happening? Once that is done, once these competent rocks are there and you fold them, then all of a sudden, of course, the deformation goes to the hard bodies. And that's where the mineralization will start basically developing, because the hard bodies then crack and they produce this pattern of veining, literally. So it's a series of veins that are formed in this tourmaline-rich rock. So the boron, the sodium, and all that goes to these sediments, and it's forming a very hard series of bodies, and it cracks them because we're folding them. So a very different mode of operation here to deform the rocks and to absorb the gold into the story. So we don't have a Cadillac break here. This is like incremental strain, incremental folding in a sedimentary package right next to a granite, which itself had hydrothermalized its host rocks, right? So it's a series of events that you don't see very much, I think, so far anyway, in the Archean. And now we're transiting back to the southeast corner, again in the Ashanti trend, to sort of revisit some of the very important characteristics of that area to compare it with the Kenyeva window. Here is now another look at that basement sedimentary contact. Okay, a series of normal faults probably that were developed right along the edge of this basement that dropped this sequence and basically created a big sedimentary basin that filled probably with volcanics at the bottom that are capped by these alluvial by these carbonaceous shales. And then one day you invert the story. So you develop this beautiful basin, deep water, anoxic, blah, 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 and you saturate with sulfur and arsenic and all you want. And then one day, so more or less this scenario, right? So you're basically creating a big fault. You're creating all these black shales, you're loading them up. They're saturated with sulfur and all kinds of other elements. And then one day you invert it. Same story. You take the fault, you invert it, you shear it back up, but at the same time you're shortening the rock. And this is what they look like. So these are completely convoluted, right? So you look at those shales, they look like they're toothpaste. So they're very, very damaged. The end of that, so this gets done once, two times, three times. So there's three fold stages that affect that same rock package. And it just gets recycled and recycled. And eventually this arsenoparite will fix the gold from whatever source you want to take it from. And it will mobilize it inside this package of rocks, particularly where the folds are developing. And the last stage of folding, which is this one, will eventually produce these beautiful shoots. So now the mineralization is going to sit in the form of shoots that are controlled completely by folding that affects this beautiful package of laminated black shales. Black shales are not that common in the Neo-Archean. They're particularly rich, they're particularly important here, and that's why this deposit or this trend is so endowed and so fertile. So that's the most endowed orogenic mine, as far as we can tell. There's 80 million ounces in this one deposit, so it's the largest of its kind. But we're going to really quickly go across this sedimentary package. So the blue here I'll come back to in a moment. We're going to we're going to travel about southwards about 100 kilometers to the south here to look at this other deposit on the other side of that blue package. So in other words, on the other side of this small package right here. Okay, and we're going to go to Wassa. And that's what Wassa looks like, even in a cartoon fashion. Very complex, extremely complex, completely different rock types. So we started off with black shales on the west side. Now we're dealing with a mixture of volcanic rocks, porphyry, whatever. So it's more like a volcanic package, but it probably sat on the basement sequence. So volcanics that were once laid on top of a basement, and it's polyphasic, you can clearly see it, and it's deformed 3 or 4 times. Those styles of deformation are manifestations of the fact that the rock had to be shoved onto a buttress multiple times and got deformed more once, twice, 3 times, 4 times. That forced the rock to roll over itself, and it took the fluids, this is metamorphism primarily, and it rolls it once, twice, 3 times, and it packs it up. So eventually the gold that was eventually trapped the first time at 2.16 billion years ago gets rolled over once, twice, 3 times, and it gets packed, and that produces a deposit for it that produces shoots again. So there's a fault there, yes, but it's not the fault that is the cause of the story. It's the folding that really packs it up. So this is a different mode of operation again. And you can see basically all the evidences. I want to draw your attention to the fact that this is the beautiful veining produced there. And it is probably this material that will, once it's formed, that will eventually get eroded. So we're on this side. So Wesley was up here. So we're now on this side. Once this package of rocks gets folded as it is, it produces this erosional material, quartz clasts. So basically beds of quartz clasts that are now accumulating with placer gold in it. It has placer gold in it that is derived from basically that source potentially, probably not from this side, but from this side, and it got dropped into the sedimentary package, which is basically a thick alluvial package of conglomerates and sandstones mixed in, an equivalent of conglomerates of Neo-Archean time, but a very different mode of operation altogether. I would claim that these sediments are produced syntectonically during compression as the whole rock mass was thrusted on top of itself, and you're creating what we call a molasse that is derived from multiple sources around itself, but now it's accumulating all its material from it. So it's collecting all gold into itself, and there's no equivalent of a conglomerate like that carrying any placer gold in Neo-Archean conglomerates. So that's a very big distinction to make. I'll finish with a couple of slides to honor the visit of our great friends from South America who are working very hard in Suriname. We'll show you a couple of exceptional deposits that we don't hear much about and that people have not considered very much in the past. However, they're really nice, very good deposits. We're in Suriname, so we're in basically South America, on the north shore of South America, south of Trinidad, if you like. Um, we're we're looking at yet another domain of Rhaetian age. We're in a large sedimentary basin, so this is the outline of the sedimentary basin. The size of the sedimentary basin is the size of the pits. It's huge, 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 huge. Siliciclastics, turbidites, whatever, and you can clearly appreciate that it's sitting right next to a volcanic package, quite diversified, but that's basically a volcanic to sedimentary sequence. So this is basically our bulk barcoding that I showed you in the previous slide. That basically goes from volcanic rocks to sedimentary packages that are enormous on top. Notice the blue rocks that are sitting in between the green and the beige. Those are clastic sediments. They're like the conglomerate that I was showing you in Ghana. So the deposits are where? I just want to show you very briefly these two, Roosevelt and Marion. Let's start with Roosevelt. And that deposit sits right at the interface between the blue rocks, the conglomerates and the sandstones, and volcanic rocks that are sitting right next to it. And that deposit has almost the same, I'd say the same endowment as Malartic. It's basically the equivalent of Malartic in terms of endowment, in terms of grade as well. It started life earlier, so unfortunately it didn't actually return as much income, but that's okay. So why is it there? It's right there, right at the contact, and I'll focus in right now. It's there because of this scenario, okay? So imagine any geological map you may have considered in the past in Neo-Archean greenstones or even Rhaetian greenstones, and that's basically the story. So you're looking at a granite here that intrudes basically siliciclastic rocks. This is sediments altogether, bounded by a structure right along the contact with volcanic rocks. And these are the deposits. So there's 8 ore bodies that are developed right in front of this pluton that intruded inside the volcanic rocks and inside that sedimentary basin. A pretty simple story, really. There's no really big structure here. There's no Cadillac break. We're far, far. There's no Cadillac break here, and yet it's the same endowment as Malartic. There's a structure, yes. So there's definitely a fault, and I'll show it to you in a moment. But I would not quantify that structure as being the equivalent of the Cadillac break, and I'll show you the evidence in a moment. Okay. So we're standing in the mine, we're looking into one of its walls, looking east, and that's the scenario. Folding. We're coming back to folding. We had folding in Ashanti, we had folding in the Kenyeba window, and some strain, of course, because folding necessarily leads to higher strain, right? The folds are not harmonic. Eventually, you're going to create breaks, and that's exactly what this spectrum shows. There's shear zones bounding the folds. So you started off basically shortening these sediments progressively against one another, shorten, shorten, shorten. You're creating all kinds of fluid flow. You're creating all kinds of veining. You're creating all kinds of fracturing. The fluid goes into it. Nothing says yet that gold will be in it, but gold does end up in it. And it actually fills all these veins, extension veins and shear veins that are themselves expressed here in the wall in this beautiful exposure. That captures this network, this framework, captures 1-2 grams per ton of gold together with sulfides in this very simple scenario. And it more or less the same story for all the ore zones that are shown on this map. And that's the process. It's that simple. And all this gold went into these beautiful folds. The one thing we know more of, and that's the vein system. So it's relatively simple. One stage of deformation, maybe a second one, but not very intense. And that's about it. One thing we're learning now, however, and I think certainly Nicole can attest to that, this scenario develops also, and I need to go back maybe to the previous slide to tell you this. Oh, no, it's not showing up here, but you see these volcanic rocks to the south here? These volcanics are basically hosting gold as well. We didn't know of that when this was developed, but there's actually volcanics that are now also hosting gold in the south of this scenario. So maybe those volcanics are also contributing to the endowment. You want to convince yourself of the nature of the structures, and I really recommend that people strongly try to report the nature of structures when they're mapping them, where they're trying to basically illustrate the mechanisms and the intensity of deformation they're working with to assess the nature of the targets that they're looking at. It's a tiny shear zone. This is the one shear zone here that has about 5 million here, the 5 million ounces nearby or in it. It's 5 meters wide. The strain, so in other words, the change in shape of any rock in it, there's a conglomerate, okay? The change in shape of the conglomerate pebbles within that conglomerate are barely changed from the original shape. So there's not much deformation in this corridor. It's definitely a profound structure. It got recycled, so there's some strain, but that's basically the nature of that structure that allows some of the influx of the fluids to produce or contribute to creating that deposit. Compared to the Abitibi, to this Cadillac Large Lake, this is a miniature structure, really minor. And I compared it with the Ashanti structure, which is 50 meters wide. So the normal magnitude, less, of course, less endowment as well. And definitely, these structures have different modes of operation. They have different magnitudes, and yet they're delivering gold. So that's, I think, a lesson learned from the Reich and from the Rosabelle deposit. Really quickly, we're going to Marion, which is about 80 kilometers east of Rosabelle. Again, we're in sediments. We're in plastics. We're in sandstones and waukes. Those are the two main rock types. And you can see them from the map. I mean, there's really nice map features delineating some beds in the waukee sequence in particular. And look at that architecture. Yes, there are some faults drawn on here, but these are miniature thrust faults. They're not big shear zones. And it's basically a megascopic fold you're looking at again. A large entry point that is plunging to this direction, and it's actually an open style fold. It's not even a tight fold or anything. And yet, this system has a lot of veining like this. So you see the very complex veining. So it took a while to form this. It didn't form overnight, of course. This is mainly forming in the actual traces of some fold closures. But this is the network that was produced by this regime of contraction plus some cross faulting. So it's folding plus cross faulting that creates local high latencies, produces this style of folding, which is very open, plus this style of veining, and you're dealing with 10 million ounces, the same size of the Arctic again, and the same grade, but not on a Cadillac break. We're in sediments again. Interesting, isn't it? And we'll terminate with one of the current project that is being worked on by Vincent, who's with us today. And this is a beautiful story. It's a fairly well known, and I'm not, of course, going to tell it as well as Vincent will. But in a nutshell, it's a different scenario. In this case, it's not sedimentary hosted as much. There's sediments around, but in this case, it's like small felsic bodies of basically small felsic plugs and intrusives that are injecting themselves into sediments and volcanic rocks. And they happen to be in, say, nearby a very high strain zone in this case. So in this case, we could eventually evoke like an analog to a Cadillac break if you want. But that package of rocks was submitted to 2 stages of deformation minimum that basically contorted it multiple times. So again, folding is a primary condition. And it's just like these felsic intrusives again, having such a competency contrast with the host rocks around themselves that starting nucleating the strain and nucleating the deformation, and the veining went through it and everything else went along with it. And it started basically because of the full polyphase folding, started nucleating all these conditions to produce beautiful plunging bodies that are actually shooting at a very shallow angle in this package of rocks that is currently delineated beautifully by this company. So a different scenario again. I'd say strain, I don't know what you would say, Vincent, but I would say the strain is moderate. I mean, it's not super high, certainly, and it seems to be sufficient, certainly, to develop a scenario like this that is quite amenable with reasonable grade as well. I mean, there's some really high grade intercepts nowadays in that particular deposit. So a different style of deformation again, rocks, structures of slightly different origins. Yes, structures for structures in greenstone terrains again. But again, I would like to invite you to reflect on the fact that these structures are born differently than some of the Neo-Archean structures. And therefore, that's why the rhiation is quite attractive, because there's more of these structures around, there's more diversity, and they tend to affect a lot of sediments, which are themselves much more amenable to deformation than volcanic rocks. Volcanic rocks can get deformed, yes, but they're much harder to shorten and strain at once, because try to buckle a basalt compared to a sediment, you'll have different products, right? So that's one of the reasons. And finally, this is a synthesis of what we know of, say, Rhaetian gold systems so far. There's at least 2 primary stages of gold mineralization in West Africa and in the Guiana Shield, and Mike Tedeschi is finalizing some papers on this, and he's published already a lot of very good material on this particular topic, so I'm borrowing from Mike. So there's definitely orogenic phases that are broken in 2 stages, related to 2 phases of deformation that are well documented, and those are clearly related to deformation. They're very short-lived stages, but they're clearly are responsible for, I would say, 80% of the endowment that we know of today. But there is clearly in other places very clear relationships to magmatic contributions, intrusion-related systems that Tremaine is working on in Guyana right now. And she's clearly demonstrated that is actually gold related to a copper magmatic intrusion related system that is growing at the moment, and there's probably more of them around. So stand by, because there's going to be more discoveries of these types in the near future, certainly in Rhaetian. So I think that's in a nutshell what I wanted to share with you today. Thank you.